Why don't we feel the clothes on our body after wearing them? The touch is very much there. It's almost on the entire body, and yet we are not made aware of that touch sensation. Why is that? On the other extreme, we have another example where if there is a painful situation in the body, even if it's a very small painful condition somewhere in the body, it keeps us awake through the night. It does not allow us to fall asleep. It makes us conscious of that painful situation, even if it's a very small situation in the body. Why is that? Why are these two extremes and how they are beneficial to the body? I will add one more example for this video, and that is, if you are wearing a hat, initially you feel that sensation over the head, but then the sensation stops. And then when you remove the hat, for some time, you still feel that sensation around your head, although hat has been removed. So, what are these examples suggesting? Well, this video is on a short property in the sensory nervous system, and the property is called as receptor adaptation. All these examples can be explained on the basis of receptor adaptation, and the video is on receptor adaptation. Before we proceed, let me just remind you, we have started new sections on our YouTube channel, graph-based discussions and clinical case-based MCQ discussions. Apart from that, there is everyday MCQ uploads, and therefore, why not subscribe to the channel? All right. First things first, let's differentiate between the two terms, accommodation and adaptation. There is something common between the two, and therefore I have chosen to compare the two. What is membrane accommodation? If your stimulus is too weak, or if it is a slowly rising intensity stimulus, then the membrane will cross the threshold, and yet action potential spike will not be generated. No response by the nerve membrane. This is called as membrane accommodation. Because the stimulus intensity was slowly rising, it does not make us enough sodium channels to be available for spike to be generated. And therefore, even if the threshold is crossed, yet action potential fails to develop. What is receptor adaptation? Now in this, initially the receptor responds and action potentials are generated in the sensory neuron, but the receptor adapts to the stimulus and then it stops generating action potentials in the sensory neuron. So the difference is, in accommodation, not even single action potential is generated. In receptor adaptation, initially action potentials are generated, and later on, even if stimulus continues, no action potentials are generated. So that having been said, now let's talk about the today's topic, and that is receptor adaptation. What is receptor adaptation? In the simple terms, when you apply a stimulus, the receptor initially responds. It will generate the receptor potential, and a train of action potentials will be generated in the sensory neuron, which starts from the receptor. But the receptor adapts to the stimulus. That is, even if the stimulus continues, the receptor does not generate, later on, it does not generate any receptor potential, and no action potential will be sent in the sensory neuron. That's called as receptor adaptation. Based on this property of receptors in the sensory system, there are three types of receptors. One, the rapidly adapting receptors. They adapt very quickly to the stimulus. They are also called as phasic receptors. Two, slowly adapting receptors. And three, non-adapting receptors, also called as tonic receptors. Now let's have a look at them one by one. At the end of the video, I'm going to give you an example of all three receptors put into effect in one single condition. Okay, now here is a receptor which is rapidly adapting receptor shown by a representative diagram. The stimulus was applied stimulus increased in the intensity and reaches peak, and then it was continuously applied for some time. What you can see here is initially the receptor does respond. That means impulse traffic was generated in the sensory neuron which is attached to the which starts from the receptor. But with the continued application at the same intensity, the receptor has stopped responding, and there is no response in the sensory neuron. And the second part, again, second part is also important. When the continuously applied stimulus was removed, you can see here, again there was receptor response and impulse traffic was generated briefly in the sensory neuron which starts from the receptor. So this is how a rapidly adapting receptor behaves. Let's take these two parts one by one. First part, when the stimulus is applied, the receptor responds briefly and then it stops responding. The receptor has adapted rapidly to the stimulus. So even though stimulus continues, but the receptor will not respond. Now, what is the importance of this particular property? There are numerous sensory stimuli which are applied, which are falling on our body on a minute-to-minute, moment-to-moment basis throughout the day. And more than 90% of those stimuli are unimportant stimuli to be ignored. They are not so important. So, receptor adapts means what? It does not send impulses to the cortex. Cortex is not burdened with unnecessary information. And that is what happens with the first example that I gave, the clothes. Rapidly adapting mechanoreceptors in the skin. So initially you might feel the touch of clothes, but then even if the touch continues, we stop getting that information in our sensory cortex. It's an unimportant stimulus or unimportant information. The clothes are there, they are there. I mean, why to unnecessarily convey to the cortex again and again? So receptor adapts and the information is not sent to the cortex. Information is stopped at the periphery because it is unimportant information. That's part number one of the receptor adaptation, the property. And the second part is when the stimulus was applied, the receptor has responded, and then with a continuous same intensity stimulus, no response by the receptor. Again, when the stimulus was removed, again the receptor responded, which means that the receptor is responding only to the changes in the environment rather than a steady environment. Do you get this? Stimulus was applied. That was some change in the environment. The receptor responded and it conveyed to the sensory cortex. There is some change. Then the stimulus was continuous. There is no change as such. So receptor stops bothering the cortex. And then the stimulus was removed. Again there is a change in the environment. This is a change. Therefore, again the sensory cortex is conveyed. Receptor sends the signals to the sensory cortex. There is a change in environment again. So, the second part of this story is that the rapidly adapting receptor is only to convey the change in the environment rather than a steady environment. Let's have a look at this property. Okay, when a stimulus is applied, initially the receptor responds, but with the continued application of the same stimulus, with the same intensity, the receptor stops responding, it got adapted. And when a continuous stimulus is removed, again the receptor responds briefly, so that means the receptor is conveying the changes in the environment rather than a steady environment. Alright, and let's also see the significance. We have already talked about it. Unimportant sensory stimuli. So, cortex is not unnecessarily burdened with those unnecessary informations. And the second part, receptor responds only to the changes in the environment rather than a steady environment. Right. Now coming to the important part. What is the mechanism of receptor adaptation? The best studied receptor is a Pacinian corpuscle. Well, you can see here that the Pacinian corpuscle, a typical Pacinian corpuscle is shown in the diagram, and a sensory neuron, a myelinated sensory neuron, starting from the core of the receptor and going to the spinal cord. All right. The Pacinian corpuscle has a lamellar organization. You can see the lamellae, onion-like lamellae can be seen, and the core is filled with viscous material or viscoelastic material. That's a typical Pacinian corpuscle. Now, when I apply the stimulus, there is mechanically gated sodium channel or mechanically gated cation channel. I apply the stimulus, the channel opens, there is an influx of cations, influx of sodium. It will generate the receptor potential, and the impulse traffic will be generated in this sensory neuron, and it will go to the sensory cortex. I mean, the information will go all the way to the sensory cortex. So change happened when you applied the stimulus, the change was conveyed to the sensory cortex. But then, if the stimulus continues at the same intensity, what really happens is the viscoelastic material inside gets redistributed, and the lamellar organization, which was initially changed by the stimulus, it will again reorganize in such a way that the cation channel is blocked, or it is closed, and no influx of cations, and therefore no receptor potential and no impulse traffic in the sensory neuron. The receptor has adapted. So even if you are continuously applying the stimulus, because now there is a redistribution of that viscoelastic material, it will no more allow the sodium channel to open even with the stimulus being applied, and therefore we will say receptor has got adapted. All right. So mechanism is related to that viscoelastic material getting redistributed and the lamellar organization getting reorganized in order to close that cation channel. And then if the stimulus was continuously being applied and it is suddenly removed, the stimulus stops. What happens again? Again, there will be redistribution of viscoelastic material in such a way that the cation channel will open up once again, and there will be generation or influx of sodium and generation of receptor potential, and brief train of action potentials will be sent in the sensory neuron, will be conveyed to the cortex that some change has again occurred in the environment. So this is the mechanism of adaptation by Pacinian corpuscle or any rapidly adapting receptor. All right. So most rapidly adapting mechanoreceptor, that is Pacinian corpuscle, and therefore it is best suited to detect the sense of vibration. Think of vibration as a mechanical stimulus, stimulus being applied, a change in the environment, stimulus being removed. I mean, vibration happens like this. So stimulus applied, removed, applied, removed. Constantly the changes are happening and detected by the Pacinian corpuscle very rapidly, and therefore it is best suited to detect the sense of vibration, particularly in the frequency of 200 Hz. All right. Now coming to the slowly adapting receptors. Some mechanoreceptors are slowly adapting mechanoreceptors, particularly the Merkel disc or Ruffini's corpuscle or Ruffini's end organ as they call it. Stimulus applied, initially a train of action potential generated, but you see stimulus continues and the action potential frequency has declined. I mean, over a period it slows down and in fact it stops. The action potential generation has stopped in the sensory neuron. So this receptor did adopt, but adapted slowly. So location of touch is detected best by such receptors, because you don't want the receptor to adapt rapidly. You want the location of the touch to be clearly identified, and therefore it does adapt, but it adapts slowly. So pressure receptors also adapt slowly. And now coming to the third part, that is we talked about the pain. Even if there is small painful condition in the body, it keeps us awake through the night. It constantly makes us conscious of that painful condition. The pain receptors are also called as tonic receptors because they don't adapt. You can see here in the diagram that the stimulus was applied and there is a steady impulse traffic generated in the sensory neuron. Throughout the stimulus being applied, painful stimulus, impulse traffic generated, and the cortex is being informed continuously about this kind of stimulus. In fact, as a property of after discharge, even if the stimulus stops, for some time at least, the impulse traffic continues. Even if the painful stimulus is removed, for some time you continue to feel that pain sensation. So this is typical of a nociceptor. Nociceptor family is TRP superfamily, transient receptor potential superfamily, and the member is vanilloid receptor. Now pain is indicative of some kind of a tissue damage, some kind of a harm, damage is going on to the tissues, and that is how the pain is generated. And therefore pain receptor does not adapt. It continues to send a signal to the sensory cortex that there is some damage, some harm going on, and you need to remove that damage. And therefore pain receptor does not adapt. It's a tonic, non-adapting receptor, means a very important stimulus. We have seen unimportant stimuli like clothes on the body, unimportant information stopped at the periphery, cortex not made constantly conscious of it. But pain, important stimulus, some damage going on, you need to take some action about it, remove the damaging stimulus, and therefore that sensation is continuously sent to the cortex. The pain receptor does not adapt. We might have thought that if the pain receptor also was adapting, how good it would be that we wouldn't feel the pain. But no, in fact, it is bothersome because it is telling you that you should remove that stimulus. You should stop that damage to the tissue, and that's how pain receptor is a non-adapting or tonic receptor. It shows tonic discharge. So compare the two, the phasic burst of action potentials shown by the rapidly adapting receptor versus tonic, slow level but continuous type of a discharge by tonic receptors. Now finally, I'll tell you another interesting situation in the body which includes all three types of receptors. If you are seated in a chair for long duration, there is a touch, there is a pressure. Now you won't feel the touch, you won't feel the pressure of the chair after a while. So rapidly adapting, slowly adapting receptors are involved in this situation. But do you know that you constantly, not constantly but intermittently, I would say, change the position of your seating? Why is that? It's because the pressure on the body part compresses the blood vessels, and after a while that area is likely to be ischemic, and a slight ischemia will generate a pain, a small painful sensation, and that will be sent to the cortex, and you would subconsciously change your position, seated position, so that the part which was pressurized previously will now be relieved, and that changes your seating position so as to relieve that ischemic pain in that region. So all three receptors are involved in this particular situation. Or like in the case of sleep, you are sleeping on the mattress, there is a touch, there is a pressure, but even during sleep you make the movements. Now in this case there is no consciousness involved as such, but since the receptors adapt, there is no there is no sensation reaching the consciousness, at least of the touch and the pressure of the mattress. So amazing physiology, and many more such videos will come particularly in the nervous system.